math and beats. More videos. In this video, we're going to be looking at proof by induction. So we want to prove statements using a certain technique called induction. And on the previous video, we investigated what inductive reasoning was. So now we're going to apply that to the mathematical situation. So to begin, we must talk about what the principle of mathematical induction is. Well, this is the technique in which we use inductive reasoning here to actually prove a statement. And we're going to primarily use this when we have some type of statement, say P of X, either true or false, and we hypothesize whether or not that statement is true for all positive integers X. And so there's two steps to this. So just make sure this is for a situation in which we have a statement and we are claiming that it is true for all positive integers X. That's when we use this situation. Okay, now, the first of the two steps in which we are going to prove something, some statement using mathematical induction, is this base case. We must show that the base case is true. What does that mean? Well, if we are claiming that some statement is true for all positive integers X up here, that's X is 1, 2, 3, and so on, then the base case correlates to the very smallest of these values of X. So in general, it'd be X is 1, or it might be X is 0 or 2, just depending on where we start our index. But in general, we start at 1. So we show it's true, the statement that we're claiming to be true, show it's true for the very smallest value of X, in this case 1. And so we show that's true. We just plug in 1 into the statement, and then if it's true, we move on to the second case, which is showing the inductive step. This inductive step is a little more involved, and once we show the base case to be true, we now assume that P of X is true for all values X equal to K. So just the general situation is true. We assume that to be true, and then we have a goal. The goal here is to show that by assuming P of K is true for all K, then we want to show that it is then implied that P of K plus 1 is true. If we were able to show this to be true, then we would prove that P of X is true for all values of X using the principle of mathematical induction. So you kind of think about what this means. We try to assume, we show it's true with the first case, then we assume it's true for all such cases, and then assuming that it's always true, we can show, no matter what, that the next value of X is also true. All right, we're going to dissect how this works via an example here. In this example, we're going to show or prove that this function here, f of x is 2x plus 1, is always a positive odd integer. And here we're going to assume that x only takes on values which are positive integers. X is 1, 2, 3, and so on. So we want to show that, and we're going to do this by using mathematical induction. So what does that mean? Well, first of all, we are going to create a sentence. 2x plus 1 is a positive odd integer, which we're trying to show is true. Let's let P of X represent the truth value of that statement. And our goal is to show it's always true. In other words, P of X is true for all X. So we got that statement set up. So now we do the base case, the step 1. Smallest value of X in this situation is X is 1, since we are assuming that X only takes on positive integer values. Then the first situation, the base case, is to plug in that value of x as 1 into our statement and show that it's true. So that's what is shown right here, is that, okay, we plugged in x is 1 into the statement, which, remember, we were calling f of x 2x plus 1. I plug that in, we get 2 times 1 plus 1, which is 3, and 3 is a positive odd integer, so this statement is true for the base case. Check. That means we're going to move on to the inductive step. And so we just showed the base case is true, and now we're supposed to assume that is always true. The general situation, p of x is true for all values of x equal to some number, whatever it might be, k. Now our goal in this step is to show that if we assume this for all values of k, p of k is true, then we can get the implication that p of k plus 1 also true. So we want to show that assuming p of x is true always, it implies that p of x plus 1 is true, the inductive step. So here's a lot of stuff going on here. Let's dissect this. So we got, what we do is just we plug in general value, k, any positive integer in general. Then we get the expression f of k is 2k plus 1, which is really the same thing that we started with, just replacing x with k. And now we're going to assume that's always a positive odd integer. We want to show that p of k plus 1 is also true. So we're like, well, what's p of k plus 1? Well, that's just plugging k plus 1 into the function f of x. So remember, just replace the variable with k plus 1, and we get this expression 2 times the quantity k plus 1 plus 1. And then just distributing and collecting like terms, we get that it's 2k plus 2 plus 1, which we could rewrite as 2k plus 1 plus 2, or f of k plus 2, because f of k is right there. That's f of k. So plus another 2. And it should be clear now that this is a positive odd integer, because we're assuming f of k is a positive odd integer. And if we add the number 2 to a positive odd integer, then we're always going to get another odd integer. Just go by 2. 7 plus 2, 9. 9 plus 11, 9 plus 2, 11, and so on. So we have shown it to be true. We have shown that by assuming the statement is true, it implies that the statement is true for the next value right after it as its input. So we have proven this by induction, proven the statement by the principle of mathematical induction. We've shown that the statement that we hypothesized, the statement 2x plus 1 is always a positive odd integer. It's true for all x. And you see this little square here at the end. It's a symbol that we can use to conclude a proof. In math, really, you can use any symbol you like, but that's a standard symbol. Okay, so to wrap up this video, we are going to do one more example, which is a little more involved, and it's an example of trying to prove a statement using the principle of mathematical induction. So that's what we want to do here. Use the principle of mathematical induction. Forgot about that word there. To prove that for all positive integers n, this statement here is true. So basically, what does that statement say? If you add up so many positive odd integers, that sum on the left-hand side is equal to the square of the number for which you are stopping at. We want to show that's true. So that means, using induction, we're going to start with the base case, which here would be n is 1, since n is assumed to be a positive integer. And if you plug that in, then left-hand side of that equation is going to just be 2 times 1 minus 1, which is 1. In other words, when n is 1, we don't even add up anything. We just have the first term, because 2n minus 1 is where you stop adding, and that happens to be the very first number. So left-hand side is 1. All right, what about right-hand side? Well, again, plug in n is 1 to the right-hand side, we get 1 squared, which is also 1. Hence, the statement is true. true for the base case. All right. That means we got to now do the inductive step. Inductive step, which means now that the base case is true, we're going to assume it's true for really any positive integer n. So we're going to, let's first of all say something like, how about let's let p of n be the statement 1 plus 3 plus 5 plus 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 all the way down to 2n minus 1. Let's let that be that equation there, so the truth value of that. Then we assume that for all n equal to k, p of k is true. That's our assumption in the inductive step. We want to show in this step that assuming that p of k is always true, this always implies that p of k plus 1 is true. So what is p of k plus 1 anyways? Well, p of k plus 1, we're going to replace the n in our equation, p of n, with k plus 1. First, let's look at the left-hand side. It's going to be 1 plus 3 plus 5 plus plus plus. Well, we already added all the way down to 2k minus 1. And then the next one after that is going to be 2 times the quantity, k plus 1, minus 1. And then just to rewrite this, that's 1 plus 3 plus 5 plus plus plus, all the way down to 2k minus 1. And then just distributing and collecting like terms there, you get a plus a 2k plus 1. Notice that these first k terms is just really k squared because we're assuming that p of k is always true. So really, the left-hand side there is k squared plus the quantity 2k plus 1. What about the right-hand side? Well, just replace n with k plus 1 again. We're going to get k plus 1 quantity squared, which is k squared plus the quantity 2k plus 1. Of course, that's k squared plus quantity 2k plus 1. And guess what? Left side, right side are the same. Hence, p of k plus 1 is a true statement, assuming that p of k is a true statement. So we should wrap this up. We've proven it now. We've proven the original statement to be true, so we should make some conclusion by the principle of mathematical induction that 1 plus 3 plus 5 plus 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 all the way down to 2n minus 1, that's always the same as n squared. Throw that little square thing at the end. We're done. We did it. And that is the end of the video. Hopefully it helped you understand a little bit better what proof by induction is in mathematics. Now it's time for us to build the next video. Later.